All right, so we're starting chapter 3 today, and in chapter 3, we're covering basically two topics. We're covering matter and we're covering energy. And if you look at kind of what science is and what chemistry ultimately aims to discuss, you're going to find that matter is one big component of that, and energy is the other big component of that. And so we're going to discuss both in this chapter this week as we start to kind of move our way toward a general understanding of chemistry as a science, and then we'll get into some more of the nitty-gritties as we move a little bit further along. So we need to start with this concept here. Matter itself. By definition, chemistry is the study of matter and its interactions. And by definition, matter is anything that occupies space and has mass. So basically, any physical object is made up of matter. So that means that every object on this desk is made up of matter. The desks that you're sitting at, the chairs you're sitting upon, those are made out of matter. The computers that you're typing into, the notebooks that you're writing on, those are made out of matter. Basically, anything physical, including yourselves, is made up of matter. But here's an important distinction that we have to make. Energy itself is not material. Energy, like heat, light, we can't quantify energy using mass. We can't quantify energy using volume. It's something completely different. And so one of the things that we're going to have to put into perspective here in this chapter is that separation of these two categories. When we are talking about things that are physical stuff, that's matter. When we are talking about the non-physical parts of chemical reactions, heat, light, sound, other intangible kinds of things like that, that's energy. Two separate areas. Matter is the physical world. Energy is the non-physical component. But yet plays a significant role in how those physical components interact with each other. So our primary discussion today is going to be over matter itself. So I'm going to pose you this question. It's a discussion question here in Pear Deck. What are some ways that we can take that idea of the physical universe and put it into some categories, some groups, to help us to kind of chunk out different parts of the physical universe into groups that have some common themes? So no right answer or wrong answer here. Just want to see where your head's at. What are some ways that we can put matter into groups? If you have not responded yet, go ahead and keep working on it. let's take a look at what some people are saying. So we've got solids, liquid, and gases. We're talking about sizes. Okay, we're getting into some properties here. Okay, that's a good one. Breaking things into living and non-living. Some more about phases. Getting into the subatomic. Phases. Living and non-living, that's good as well. Breaking into groups that way. Okay. Some really good responses in here. And most of us kind of trending toward phases of matter, which is perfectly acceptable. It's a very easy way of classifying. In fact, that's kind of what I anticipated that we would talk about first, because that tends to be the easiest way to go. So one way that we can classify matter is in phases. We can classify matter by its so-called states. 3 states of matter, we know: solid, liquid, and gas. We have a discussion about that 4th phase of matter, the plasma phase. However, plasma doesn't play on, we don't see it very often, has very, very limited kinds of circumstances for us. But in those 3 phases of matter, we can look at them a little bit more closely. So, for example, a solid. Solids we can define by the fact that they have a defined shape and a defined volume. Liquids, on the other hand, have a defined volume, but their shape changes as we go from container to container to container. You know this phenomenon quite well. Take a gallon of milk out of the refrigerator or a bottle of juice. It's the shape of the container that we put it into. You pour it into a glass, it takes on the shape of the glass. You pour it from a glass into a mug, it takes on the shape of the mug. Liquids change shapes. But the amount of milk, the amount of juice that we put into each one of those containers, that doesn't change at all. The only thing that might change is if you put too much liquid into a glass and it overflows, but that's a completely different concept. Gases, on the other hand, have no defined volume and no defined shape. They will automatically take the shape and volume of whatever container that you put them into. Now, in these diagrams, we've got an approximation of what the different phases look like at the molecular level. And so I ask you this question, not as a Pear Deck question, but as a general question overall for discussion here. If I look at the phase of gas, what about that particular phase and the way that the molecules are arranged in that phase would lead you to believe these properties about a gas? This sample of gas, how would we describe the molecules in that sample of gas? Are they close together or are they far apart? They're far apart, okay? Because they are so far apart, when we move that sample of gas from one container to a different container to another container, the space in between them just shifts. Maybe they get a little bit closer together in a container that's this size compared to a container that is this size. But because the molecules themselves aren't actually touching each other, all that's going to happen is it's just going to flex. It's just going to move from one container to another, to another, to another, and it's not really going to change much. And that's why gases are so versatile in terms of that property. I put this gas from a small container into a large container, it just expands to fill up the large container. Why? Because the molecules aren't touching each other. And since they're not touching each other, they can move it freely to fill up whatever container they're in. In the solid and the liquid, they're all touching each other, right? Each one of those molecules is touching more molecules. So when I move it from one container to another, those molecules have to stay touching. So as a result, its volume doesn't change. Because the state that it's in is going to lend itself to keeping all of those molecules associated with each other. All of those molecules touching each other. So as a result, it's got a consistent volume. And that's true both in the liquid phase and in the solid phase. That touching makes a difference. Now, what's the difference between a solid and a liquid? Kind of hard to see from the diagram. But one of the things that we can say about solids and liquids comes in its motion. The solids are packed together just a little bit tighter than the liquids are. And as a result of that packing together just a little bit tighter, it restricts the movement of the solid. The solid particles are really only able to vibrate, or in this case, it talks about oscillation, moving back and forth. It sticks in one spot and kind of vibrates around that spot. It doesn't move from here to there and all around. But a liquid, those liquid molecules are actually just far enough apart from each other that they can slip over each other. And in being able to slip over each other, they've got a little bit more freedom of movement. And for that reason, those molecules aren't fixed in place. And so we can't say that they have a consistent shape. Because the molecule that's over here has the freedom to move over here. Whereas that solid particle that's over here, it's just going to shake here and never move from this spot. And that's really the difference at the molecular level between the solid, the liquid, and the gas. It comes down to two ideas: spacing and freedom of motion. In a gas, they're widely spaced, so they have almost infinite freedom of motion. And that's why they don't have a defined shape. That's why they don't have a defined volume. In a liquid, we have freedom of motion, but the spacing is very packed close. So as a result, defined volume because of that close packing, but not a defined shape because of that freedom of motion. Solid, restricted movement, everything's packed together really closely. You're gonna have a defined shape, you're gonna have a defined volume. So table 3.1 in your book kind of summarizes all of this contextually in terms of words. And takes these pictures and kind of summarizes them. So again, you can see how the slight differences in properties at the molecular level show up in terms of properties at the level that we can see. But that's just one type of classification. Now, some of you in that discussion question alluded to a different type of classification. Classification by type, not just by phase of matter. So what I want you to do If you have the ability in your notes to create a flow chart of some sort, go ahead and do so. If you don't, try to keep things up on paper. We're going to make a flow chart to discuss how to classify matter based upon composition, not just on form. So starting at the very top here, we're talking about matter. Now, matter is able to split into two different subgroups. On one side, we have what are called pure substances. Now, why are pure substances called pure substances? In a pure substance, every particle of that given substance is the same at the molecular or atomic level, depending upon which pure substance we're talking about. Because of that, we describe pure substances as having a uniform composition. Sometimes this is referred to as a constant composition. There's a scientific law, the law of constant composition, that talks about this very phenomenon in compounds in particular. So that's one half of the discussion, the pure substances. Pure substances being pure because at the atomic level, at the molecular level, if I have a sample of this substance, every single one of those particles is going to look exactly the same. They're all going to have the same physical properties. They're all going to have the same chemical properties. Now we can split this category into two parts as well. And these are terms that we're definitely probably more familiar with. The elements and the compounds. The primary difference between these are the number of different types of atoms that are present. For elements, it's simple. We only have one type of atom in an elemental state. Now, in future chapters, we'll get into more about what the atom looks like and how we can tell one atom apart from another in terms of, well, this is an atom of silver versus this is an atom of lead or copper or bismuth or anything else. For right now, we can focus on just that idea. In an elemental sample, we're looking at one type of atom. In a compound, in a compound, we've got to concern ourselves with a couple of other things. First of all, compounds are made out of two or more types of atoms. And those atoms in a compound are chemically combined. And in those chemical compounds, we will always have a fixed ratio of one element to another. That's where the constant composition part comes in. So if I'm looking at carbon dioxide, for example, carbon dioxide is characterized by having one carbon and two oxygens chemically combined together in a certain way. If I change that ratio, if I turn from one carbon, two oxygens to one carbon, one oxygen, I have a completely different compound, completely different properties. Just like water. H2O, that's water. Two hydrogens, one oxygen. Change that to H2O2, I go from something that sustains your life to something that ends your life. Those little differences in formula make big differences sometimes in chemical reactivity. Big differences in terms of physical properties. Something in that case, big differences in terms of toxicity. Hydrogen peroxide will eat you from the inside out. Water is necessary for you to live. So that's the pure substances side of the spectrum here. And again, pure substances, we're looking at that constant composition kind of idea. On the other side, we have what are called mixtures. Key characteristics of mixtures. For one, there is a lack of uniformity inside of mixtures. For another, these are physical combinations of substances. So one of the easiest things to get mixed up in your head is because some mixtures have a uniformity of appearance, it's easy to confuse them with compounds because compounds also have a uniformity of appearance. How do I know the difference between the two? Well, a mixture is a physical combination. Since it's a physical combination that brings the mixture together, it's a physical process that can drive them apart as well. Simple example. Let's say that we are making Kool-Aid. Kool-Aid's a 3-ingredient drink. You've got sugar, you've got water, you've got the flavor packet. Now, to put them together, all I need to do is just literally toss them together and stir. To separate them from each other, I basically just have to undo that process. Now, that doesn't mean I stir in the opposite direction. It means I have to get the water out. So if I boil the water off, I can get the sugar in the flavor packet, and then I can use another way to get the flavor packet out as well. But that's what I would do. Physical process brought them together. Physical process can tear them apart. I can't do that with a compound. Compound is brought together by a chemical process. So if I want to make water out of hydrogen and oxygen, I literally have to ignite it. I got to take hydrogen and I got to blow it up. So if a chemical process brings them together, a chemical process also has to be what separates them. And the chemical process in water is called hydrolysis. You basically shock the living daylights out of the water until hydrogen and oxygen come out on both sides. In a small scale form, that's what happens in a fuel cell. In a fuel cell, you burn hydrogen in oxygen to make water, and then you use electricity to shock the water to get the hydrogen and oxygen back to burn in the first place. So that's what a mixture is. Now, mixtures can be broken into subtopics as well. These subtopics are not nearly as complicated. We have the homogeneous mixture, and we have the heterogeneous mixture. Really, the only difference between these two is how they look. Homogeneous mixtures appear uniform. Heterogeneous mixtures do not. So again, homogeneous mixtures often confused with compound because of that uniformity of appearance. But we have to remember, even if it has a uniform appearance, it has a lack of uniformity from a chemical standpoint. So taking to example that Kool-Aid again. There are lots of ways to make Kool-Aid. You can follow the directions on the package, or you can go your own way. You follow the directions on the package, it tells you you need exactly this much sugar, exactly this much water, and the flavor packet. You do it your own way, you can add more sugar, you can add less sugar, and honestly, you give your Kool-Aid to a bunch of people, and so long as you don't deviate too much from the recipe, they go, oh yeah, that's Kool-Aid. So if you add the full cup like they tell you to, or if you add 3/4 of a cup of sugar, you probably aren't going to notice the difference. Yet you're going to still call it Kool-Aid. And so that's what that lack of uniformity is in the mixture. I can take these same ingredients, combine them together in a slightly different way, with slightly different ratios of each ingredient, and still the same stuff. Heterogeneous mixtures, lack of uniform appearance. We're talking about things like garden salad, for example. You make a garden salad, you got lettuce, you got tomatoes, you've got cucumbers, you've got some other stuff. Throw them all into a bowl, mix them together. I can still pick out, hey, look, that's lettuce, that's cucumber, that's tomato. It's easy to see all the different components. You can't quite do the same thing with Kool-Aid, right? I can't look at Kool-Aid and say, okay, well, that's the sugar, and that's the flavor, and that's the water. It's all mixed together. It all looks the same. I can't tell one component from the others. So this is this is another way of looking at matter. And looking at from this particular perspective of composition. And if you follow in the notes here, you'll see that much of the stuff that we put into that flow chart is also in these slides. So if you want to go back and look at the slides later on, you can see the same kind of information there. All right. Let's see if we picked up anything along the way. I've got 5 mixtures here. I want you to identify them as either being homogeneous or heterogeneous. For homogeneous, enter in HO. For heterogeneous, enter in HE. Just enter in as a string of characters. Ho, ho, he, ho, or whatever you come up with. Okay, so looking at this, we're talking about mixtures and we're trying to classify them in different categories. We need to be thinking about things from the perspective of appearance. Does this substance have a uniform appearance or does it have a non-uniform appearance? So for tap water, hopefully you came up with this. Tap water better have a homogeneous appearance or else we've got some really bad problems. A sample of ocean water. You might be tempted to say the same thing here, but you have to remember when you go to the ocean, take a scoop out of it, you're probably going to get sand in there. You're probably going to get some seaweed or algae. You're going to get other things besides the water itself. And so those other things you should be able to pick out and definitely not appear uniform. So that's why it would be heterogeneous. The air that we're breathing right now is definitely homogeneous. I cannot tell the difference between any of the many different gases that I'm breathing in right now. They all appear to be the same. Brass is an alloy when you mix brass together. So copper is kind of orangish in color. Zinc is silvery white. Brass is kind of a yellow color. The mixture of the two. Can't tell one component of it from the other. It's homogeneous. Potting soil, on the other hand, that would be heterogeneous. Inside of potting soil, you're going to find the different kinds of parts of it. You're going to find the plant food, little white specks. You're going to find the dirt itself. Inside of the dirt, you're going to find little stones as well as the dirt itself. So lots of different components. You can see all the different components. It's definitely not uniform. Right. Any questions with this grouping? All right, let's take a look at another. Five different substances here. Classify them as either element, compound, or mixture. And again, just make a string of characters. All right, so from looking at letter A, I can see each each thing in A is the same. You've got one black dot and one red dot. So we know it's a pure substance because every one of those particles is identical. This is a compound because the black and the red would represent different elements. And so I've got two different elements in the same substance. That's a compound. Letter B might have tripped you up. This is an element. Now, you may be asking, well, how is it an element if it's got more than one atom? You got to remember, the key word there isn't more than one atom, it's more than one type of atom. Those two atoms in that molecule are the same. And so this is an example of what we call a molecular element. Molecular elements do exist, especially among non-metals, where it's very possible that we would have multiple non-metallic element samples attaching to themselves, making up rings, making up pyramids, making up tetrahedrons, or just making up simple molecules like these in order to gain some stability. Letter C is a mixture. It's a mixture of two different elements, the blue element, which is probably nitrogen, and the black element, which is probably carbon. Letter D is also a mixture. Here I have a mixture of what is probably elements of carbon as well as carbon monoxide, the compound. And in letter E, I also have a mixture, where I've got a mixture of two different compounds. Got the carbon monoxide compound there, and I've got the probably sulfur trioxide there. Right. Any questions with this one here? Okay, so with our last few minutes here, we're going to talk a little bit about properties and changes. And what we don't get through today here, it is in your reading, and it's pretty straightforward. So if you understand what I'm talking about in terms of physical versus chemical properties, you're going to understand what we're talking about when we talk about physical versus chemical changes, because they kind of go hand in hand with each other. When we are describing properties, we basically categorize properties into two groups. There are physical properties. These are things that we can observe, and in observing these properties, we don't change the substance itself. So common physical properties are things like sensory things, sight. So I can observe that this particular object is hard, or that the color of this desk is gray, or that the words on the screen are black. So colors, density, hardness, malleability, brittleness, all of these things I can observe without actually changing the substance itself. That's what makes a physical property physical. It's something tangible that I can observe, and it doesn't change the properties of the substance at all to observe it. Chemical properties, on the other hand, are ones that, in order to observe them, a chemical change has to be taking place at the same time. And in a chemical change, the physical substance is changing at the molecular level. So as I observe charcoal burning, I'm looking at a chemical change because the charcoal is turning into carbon dioxide. And so the things that I see with that chemical change are chemical properties. So the chemical property involved there is something called flammability. Can charcoal burn? Yes, that is a chemical property. It's flammability. Does this substance oxidize? Does this other substance corrode? Does this substance react with water? those are chemical properties. The only way to observe those chemical properties is to actually observe the substance undergoing a chemical reaction. So here's a different example. Odor is a physical property. I can smell something without changing its identity. So gasoline has an odor to it. I can smell gasoline without changing anything about that gasoline. But when I ignite that gasoline, its properties change. And the reason its properties change is because the gasoline is no longer gasoline. The gasoline is now carbon dioxide and water vapor. And so I'm witnessing not only the physical changes that are happening as the gasoline ignites and as it burns and as we see steam and smoke and everything else, but also observing chemical changes in terms of that gasoline molecule no longer looks like a gasoline molecule. Now it looks like carbon dioxide molecules. Now it looks like water vapor molecules. So one last thing that I'll talk about, the idea of a physical change. So like I said, physical change, physical properties, they have a lot in common. We're talking about things that we can observe and note without changing the composition, without changing the identity of the substance. So when we observe physical changes, it's the same kind of thing. So I can observe water being poured from one bucket to another. I can observe water being spilled all over the ground. Those are all physical changes. We're just changing the form, but we're not changing the substance itself. Same thing goes when we see physical changes in the form of phase changes. I turn water into ice. The ice has nothing different about it at the chemical level compared to the water. It's still H2O, but its physical form has changed. So keep those things in mind as we're talking and as we're moving our way through the lesson and the post-lecture tonight. On your way out, give me that checkpoint. Let me know how you did with this today. And certainly let me know tonight how you feel after you've done a little bit more practice in the mastering homework. Have a great afternoon.